Bonjour, bienvenue au Centre de recherche mathématiques pour cette activité sur la modélisation en santé publique. My name is Jacques Veller. I'm a chercheur here at the CRM, and I'm very happy to introduce the speaker, Iain Moyles, who is part of the Omni network of infectious and emerging disease modeling. And this is how I discovered through this network. So Iain did his bachelor's degree at the University of Ontario Institute of Technology, which has been its name since. Then a master's and a PhD at the University of British Columbia. Then was a postdoc in Mathematics Applications Consortium for Science and Industry at the University of Limerick, and became an assistant professor at York University in 2019. And as I mentioned, he was involved in the networked efforts of handling the pandemic and modeling, infectious diseases. And I believe that this talk today will cover some of these aspects.
So, well, thank you very much. It's great to be here. This is my second time at CRM. I was here 10 years ago this year for one of the summer modeling workshops, where I think it's actually the first time I met Jacques, but he probably doesn't remember since I don't remember. Yeah, it's great to be back, and thank you to Bushra and everybody for the invitation to be here. So disease modeling kind of came new to me when the pandemic hit. I contacted people at my University of York. We have a center for disease modeling there. We have a lot of math biologists who work on this, and everyone was coming forward in their labs saying, I have PPE to donate, I have different things to donate, and of course all I could donate was my modeling skills. So I contacted the group and they said, yeah, we need people modeling infectious diseases. So I jumped in, and so that work led me different places. I did a paper with Bushra on school closures. I did a paper with Jacques on vaccinations. I'm not going to talk about either of those today, because actually what I'm going to talk about is something that came up from a conversation at our annual general meeting for the Omni network. And there was a question that one of our members asked, and that was sort of what is the trajectory of modeling, right? When you model, you think there's something new, we need to figure it out, you come up with a model, but then at some point you hand that model off to protect practitioners. They could be in public health agencies, they could be in other places. And so how does the role of modeling transition? And so what I thought I'd actually do today is just sort of take one model and push it through its different stages as the pandemic went on, and as the sort of philosophy changed for what was important and what we thought about and the kind of questions we were asking and the levels we were asking them. And so I really liked that question, and so I wanted to sort of start with the idea of modeling. And this is kind of my philosophy of it. There's two sides. There's going to be a parallel version of this in a second. And that is if you think about the application. And so what do we do with modeling is we often model because we want to understand something that's going to happen, right? In the case of infectious diseases, what is the case trajectory, or the hospitalizations, what are we expecting to happen? And we hope with a good model from there, if we understand the problem, that means we can predict something with it. Okay, and then we also hope that that prediction can lead to information, because modeling is, if things go into that, right? We put our own understanding of the world into a model, and so we may have a hypothesis for a certain mechanism of how a disease might change if it's disease modeling, and so we put in a model. If prediction that lines up, then we might actually have some information about the underlying process that we're looking at. And it's important, sort of as you head on in an application of a model, it's important to reflect back. And in the case of disease modeling, sometimes that's looking at sort of from a historical perspective, what if scenarios, so that you can sort of assess public policy or other decisions that were made regarding that application. And then there's, of course, I think our role too as mathematicians. So the application role, I think if you're a math modeler, you live in both of these diagrams. And at different points, we have end users that jump in and jump out. So often, we may be handing off models to agencies, again, public health agencies, which may want to use those models to make predictions for case numbers, for hospitalizations, for their agency, for their region. But mathematicians play a role in many ways. They play a role on the application side. But I think it's also important to realize that mathematics is important in itself in modeling. And there's a separate diagram we think about in terms of the actual model itself. And so I put science at the top, which is similar to understanding. And I think this is important. I teach our graduate modeling course at my university, and it's often a really hard course for students who are very good at mathematics. And that's because in modeling, we need to know the science. we need to know how to translate what we're observing or what we want to figure out into mathematics. And that's an important skill that mathematicians need to learn, because they know the math very well and need to learn a science so they can do that translation. And then when we have a model, we often think of the structure. And I think that's important. So we look at a model and we kind of say, is this model too complex? Is it too simple? Where do we think its problems are going to be, both as a mathematical object and in terms of its predictability power? And then there's sort of two branches as well with that, which is the analysis side. So we can look at a model and we can start to ask questions about what can we get out of this model? Do we see any patterns emerging from it that can simplify the model, either typically for computational speed, for example, if we have a very complex model. And this is really important, and I found in disease modeling work I've been doing. I'm not going to talk about this part today, but often when you have a model, you want to parameterize it. And sometimes this analysis side can really dig into the questions of identifiability. And so sometimes you see these models where they're trying to fit a parameter. And if you dig into the structure of the model, let's say we're trying to fit something in an exponential decaying phase of a model, but then the data you have is in a growth phase of the model, well, anything you get out isn't that useful necessarily, or you might get a very wide confidence interval on that parameter because your model and data aren't in the same region of interest that you're trying to map. So analysis plays a key role in understanding that. And then of course, computation, right? Often mathematicians are involved in computing models, particularly very complex models, which requires sophisticated computation tools, parallel algorithms, clustering, et cetera. And so this came up because of this conversation. I think it's really important that we have this message for the public, which is we don't just create this thing, give it to someone and go away. There are things that are always going on in the background to make modeling for a particular application better, but also to understand modeling as a subject so that we can long-term make it a better science. Okay, so the model I'm going to go through, this is around, I guess this is probably around March 2020 when I reached out. And so we kind of had this idea to come up with an SIR type model. And so down the vertical, which I have in this box, this is a sort of disease progression form of it. And so, susceptible people, S, they become exposed to the disease. And then we talked about having a pre-symptomatic phase. This is around the time when people were realizing the importance of asymptomatic transmission during COVID. And so we thought there's a phase where they are infectious, but whether they're becoming symptomatic or not, we don't know. There's going to be a period where they're infectious and haven't really shown symptoms yet, and then they'll diverge and either stay asymptomatic or they'll become symptomatic and eventually recover. And then if you go horizontally, this was this idea that was coming up because at the time all we had were non-pharmaceutical interventions. And so this is a physical distancing type idea. So you can transition left to right and reduce your contacts, or you can come backwards and increase your contacts. At the very far right, we have this M subscript, and that is this idea that we were testing, right? We were testing people and isolating them from the group. And so if you tested positive, you would come forward, and we assume, I mean, if you're susceptible, of course, you're not going to test positive. We assumed in this model that exposed people do not test positive because they're infected, but not yet infectious. Okay, and so we just assume their viral loads would be too low to detect them. And we have them the same color as the far groups. The idea of isolation, to go all the way to the right, the second last one, that's the idea of full isolation, that you're choosing to reduce your contacts and not see people. And we assume people who've tested positive are sort of, at the time at least, taken out of the system because you're told that you have this, you need to stay home for so many days. Okay, and so what we did first is we looked at this vertical transmission. So I'm just going to, because the model gets complex and more complex, I'm not going to write the equations down too much, but there's the simple SIR type model. And so this was just the vertical progression, right? So you have your susceptibles, exposed, et cetera. And what we did is we looked in the literature for parameters where we could, for things like recovery rates, exposure time, et cetera. And of course, the parameter that's always the hardest to get is this beta, which is this transmission. And so what we did instead at the time is people were talking about basic reproduction numbers, they were getting calculated. So we did the reverse thing, which is we took this simple transmission model without social distancing, the idea that before we know much about it, people are just going about their business without changing their behavior. And so we used the next generation method, or whatever your favorite method is, to compute the basic reproduction number for this model. We use the data for that and use that to infer the transmission rate, taking the assumption that asymptomatic people were half of the transmission rate of the symptomatic group. So then we wanted to build in this distancing. And so what we did is we said, okay, there's going to be two pieces of information at the time, at least, that are likely feeding people's decisions. One is what we call active cases. These are cases that get reported and as currently would test positive, or they haven't recovered yet. And in Ontario, at least, we reported those. And so this is the second one here. These are all the people who tested positive, right, and haven't yet recovered. And then we also keep track of the cumulative number of cases that have been reported. And so that's every time you test positive, you go into this, we increase this derivative on M, and those are the two pieces of information. And we use that to inform what we call our distancing function. And so K is actually the doubling rate. So you can look at the data and the trajectory, and you can estimate a doubling rate. And MA, again, is these active cases. And so we assume for both of these, there's some critical rate below which nobody will really do anything. Okay, if there's not enough cases, or if they're not doubling fast enough, nobody will do anything. And then above which you have this sort of classic Michaelis-Menten type mechanism where you grow and then you saturate up to some point, which is the maximum rate anyone could say reduce their contacts. And why we put both these structures in is because we thought, well, if cases are low, but you can see they're doubling quite quickly, then people are aware that there's going to be a lot coming, and so they might react. Similarly, if there's a large number of cases, but the doubling rate is very small, people might realize that things have subsided, and so they can sort of relax again because those active cases are just take time to recover and they're not actually growing. That's why we thought to do that. And so to go backwards, we said, well, what's going to drive people backwards is something we kind of abstractly called cost. And so we have a model and you have a parameter which involves some number of, say, dollars per day for doing this distancing when you don't have to. Okay, and so we assume the people in the 2 class who are susceptible or exposed. Again, we chose exposed to include because even though they're infected, they're not yet infectious, and they don't know they're infected and couldn't know, they would test negative. And so these are people who, in some sense, by reducing their contact structure, they're actually hurting things because they don't need to be there. They're well, they're fine, they can go to work, they can continue on their life. And so we take the maximum penalty if you're in the full isolation class, and then some reduced penalty if you're in the partial isolation class, just to compensate for the fact that you're still having some of your contacts. And so what we do is we rewrite that equation. We do some non-dimensionalization just to put it in terms of this weird thing, which is days, because we don't actually have a number what this means. What is the cost per day of someone isolating? That's a really hard thing to answer. And so what we do instead is this number actually turns out to be in terms of days. And so what the equivalent is that 1 day represents everybody in the province of Ontario isolating. Okay, so it's like an upper bound, let's say, as time goes on. And then, of course, if we happen to know that number, that actual dollar number, we could just translate it back through this scaling we did. But it's hard because, as I say at the top here, there's different costs that one endures. There's the direct financial cost of missing your job, right? If you don't have vacation days or sick days. There's also the psychological cost of missing your friends, your family, isolating, etc. And it's hard to quantify that. I know people are trying, and that's a whole other set of literature. And so what we decided is that a similar function would exist to relax, is if the cost was too high, there's some critical cost that you can endure. And we were at the time thinking of things like the Canada Recovery Benefit, etc., that was being offered. So people could stay home, and if they lost their job, they could recover some money. So there is some cost we could endure. And then above that, similarly, you'll start to go to this Michaelis-Menten type kinetic. And so what we did at the time is we measured these parameters were available. That's what I was talking about with the infectious period and the recovery period, etc. And then we just took Ontario data, that's the province that I live in, and we fit these parameters, including the testing rate. And then we took an assumption of about 50 days for the endured cost. Okay, so this was at the time. So this goes up to, I don't know, like October 2020. And remember, this is just one fitting. And it was pretty good. You know, it's not capturing some of these things, but remember, this is just one parameter that it's meant to capture all the data. And everything, of course, was changing very rapidly at the time. And so we were pretty happy with that at the time. And when we wrote that paper, which has been published, one of the reviewers said, you know, we talk about this social mobility of distancing and relaxing, but we didn't actually really have any discussion about data for that. because it's difficult. And then, of course, people are aware that there was this Google social mobility data available where they had a whole subset of areas where they were tracking location based on Google usage statistics. And of course, we want to be careful. That's not actually a measure of contact. Okay, just because you're going to the park doesn't mean you're seeing people at the park. Just because you're going to a grocery store doesn't mean there aren't additional measures which we know exist, such as the plexiglass barriers for cashiers or distancing in lines, etc. But anyway, of all these, we thought the one that we would look at was the retail and recreation, just because it probably reflected more accurately people's behavior, because some of the other ones, like grocery stores, for instance, pharmacies, these are things you will go to regardless of what's happening in the world. You need food, you need medicine if you're ill. So transit stations, they're kind of isolating to certain groups of people. For instance, if nobody's working, transit stations might not be open regardless. And then residential is always hard data to look at because a lot of it shows weird gaps on day-to-day life, simply because people leave their home and then they come back. Regardless, maybe they're going for a walk and never seeing someone, or they're going to work, etc. So we just happened to look at that one, and again, we didn't expect anything perfect, and it's not perfect, but there's a general trend we saw in our model and the mobility data. Again, this is just one value of a parameter, right? There's not some sort of breaking up of windows, which we will get to as we evolve. And so we were pretty happy with this, and then so as time went on, of course, it takes time for papers to publish, and so we said, well, what happened? So the red was where we stopped when we wrote the paper, and then time went on between that and publication. So we looked, and it actually continued to fit for a pretty good time. But unsurprisingly, the model takes off, cases explode, but of course, real cases didn't do that, right? And that's because one of the hard things with infectious disease modeling, as many people in this room probably know from doing it, is that the results of the model affect the model through the behavior, right? If you tell someone something's going to happen, they can change their outcome and adapt. And so there's this weird thing where you sort of have to model your model if you really want to get it accurately, but that's another conversation. So what we decided to do is say, okay, without changing the model to get it too complicated, what we can do is look at these windows which are informed by public policy. So these are a timeline of windows in Ontario where the government did different things, and then the far column, it's what they called it, different things of emergency lockdowns and other things. These words mosaic was this idea of certain parts of the province had certain rules and denser parts of the province had different rules. And these are approximately the timelines where these were enacted. And so the idea was to say, okay, we'll take these as discrete time windows and fit the parameters that we fit for all the data within these time windows. So that was the next step. And just looking at that data, that idea, we start to get a better fit just by taking those windows. And so that's the idea that we don't really question the mechanism behind the change. We just say there is a period of time where you expect a change because of these policy changes of the government, which of course are informed by modeling and other public health considerations. What we also had to do in that time, so we introduced this, but of course, as time went on, we know we developed pharmaceutical interventions to this disease as well, namely vaccinations. And so what we wanted to do is we wanted to include that in the model, of course. And so you see in panel A at the bottom, that's the same disease transmission model that we started with. And then in this little quote bubble C, that's that horizontal progression that we still had. And the new bubble, in some sense, is this bubble B. And this is a cyclical thing, which is everything before was in this U category, which we kind of call unvaccinated. So you haven't been injected with anything. And then the idea is you get a vaccine, and that either puts you in the V class, which is the idea you got the vaccine and it gave you the protection you expect, or we have what's called a W class, which is like not V, so it's W. And this is the idea that you got a vaccine, but maybe it didn't confer the protection that it should, or it did, it was the idea of getting a kind of a dud vaccine. And so that was how we initially started the model, just with that cyclical thing and the branching. And I'm going to show the next slide in a second, but I first want to explain how we modified the model further. And what we saw with doing that when you add vaccinations in is there's a point, which was late in fall 21, where you just cannot capture the fall wave. And so what we realized was that we needed to introduce waning immunity as well. And so we did that in a couple of ways. So one is we have natural waning immunity. So you get an infection, and after time, your antibodies wane, your protection wanes, and you can be susceptible again. But also, of course, waning from the vaccine. And then we also introduced what's called this V to W transition, and a behavioral waning. And this is this idea that we realized, and we all live this, which is you're told at some point when your vaccine, you should get a booster or something. But of course, when your protection is actually gone in real time is something you don't know. And so part of how you can interpret this W class, we called it this dud vaccine group, but really what those people are is they think they're protected, right? They got a vaccine, they think they're protected, but they're not. And so similarly, there's a period where your vaccine protection has waned, but you are still acting as if you have it, okay? And then there's some point of time passes further where you think, you know what, it's really been a long time since I've had a vaccine or I've had an infection. I probably am susceptible again. So you sort of naturally wane your behavior back to thinking you're unvaccinated and properly susceptible again. And so again, I want to emphasize why this came up is because we were fiddling around, and as we got to this fall wave, which happened in late 21, we just could not adjust the windows or the parameters or anything to capture this. And this all sounds sort of obvious probably now. You have to keep in mind at the time, there was still debate about waning immunity, right? Is people just didn't think it'd be that fast, or they weren't sure if it would be an issue at all. One of my colleagues who does a lot of immunity modeling was kind of getting laughed at different meetings for wanting to consider waning early on. They were like, don't worry about that. Waning won't be that big a deal. But what we were seeing is this fall wave, it can only be explained in some sense through this modeling structure we did, if we include waning immunity. So that's why I had to revisit that model. So this is that informed side I was talking about, how sometimes you use a model and you have all the mechanisms you think, and then you can't get the data you get. And so you have to start to question this. And of course, the most obvious answer, which is still probably true, and I live by this every day, which is all models are wrong, right? And so you shouldn't trust the model that you write down, but still, there's this idea where you can put a mechanism in that makes biological sense, waning immunity, and you can see it gets better. And it's still not perfect. I'm going to show the next slide. And it's, it's still missing some things. We're still playing with this parameter around a bit. One of the postdocs is doing a sensitivity analysis right now. But the idea is you're now, and so what was happening is you depleted the susceptible class, right? In some version, they either had a strong enough vaccine or they got infected. And so there's nobody left to infect in that fall wave. And so by putting waning immunity in, you're replenishing that class, and then you can start to see additional waves appear. And so that was really important and informed by the model. Okay, so there's some other things that you might want to compare, and I think this is always important. I have to declare I'm not really a data person. I like thinking of modeling as something independent of data that the data supports, and that modeling supports data, et cetera. And so I don't put too much stock into results where you say, okay, we fit some data and it looks good. It's like, of course it does. You fit the data. And so you want to find other things, if you can, to assess your model that is independent of the data you fit. And so we started looking for some. One is what we call the positivity rate. So this is something that was reported in our province. And that is the idea that they know how many tests they take, they know how many come back positive, and so they tell you a percentage of tests that day that came back positive. And so how we built that into the model, remember in our model, we say you only extract from the system if you test positive, so you have symptoms of COVID, or even for asymptomatic. If you have the virus, you'll get picked out. But what we said, okay, let's assume then, since we had different testing rates, we assumed that symptomatic people got tested more frequently than asymptomatic, right? Symptomatic people, if you had symptoms of COVID, you likely suspected you had it, you're going to seek out a test. Asymptomatic people, on the other hand, many of those kind of stories were, I was going to my friend's wedding for the weekend, didn't want to get anybody sick, so I thought I'd drop in for a test center, and oh my goodness, I have COVID, right? So it's a lot, it's something that kind of happens more by chance or because you're concerned. It's not something you seek out because of your symptoms. And so we said, well, what if we assume that those other groups that wouldn't test positive, so susceptible, the exposed, the pre-symptomatic, or sorry, the susceptible, exposed, and the recovered group, who, if they tested, they would just get a negative test. Let's assume they have the same testing rate as the asymptomatic people. Because of course, if you're asymptomatic, you have no idea. You're going just because you want to get a test for some reason. You think you probably don't have it. I mean, you don't have symptoms, so of course you think you don't have it. And so you're just as likely in some sense to come back negative as you are positive. And so we said, let's have that rate be the same. So we call this total test thing, which is now adding on that testing rate to all of these classes along with the symptomatic testing rate. And then of course, what we do for the daily test positive rate is we said, let's take the new cases, which are the difference in total cases between today and yesterday, and divide it by these total tests that we define, and we'll call that the test positivity rate. The other thing we can look at is serological studies. So there's a lot of data, particularly from Canadian Blood Services, because of course they regularly collect blood for donation. And so they were taking blood that was donated and they were looking for antibodies in it, and they were able to discern between infection and vaccination. And so they report this, and it's sort of meant to be a proxy, people believe, for like true infection in a way, because you're going to donate blood and whether you were asymptomatic or not. And they did ask in the survey if you thought you had COVID or not. So getting a sense of that. And so we don't measure that directly, of course, but in some sense we said, well, one proxy for that is the recovered group, right? In the sense that if someone in the recovered group gave blood, they could present these antibodies. Now, there's some asterisks there, right? Of course, just because you had an infection doesn't mean you will what's called seroconvert, which is produce antibodies. There's some evidence that T cells can stop infection, for instance. So it's possible to not. It's also possible that you take this seroprevalence test and get a negative, false negative, et cetera. So anyway, but that's something we said we could take as a proxy. And so the first one for a long time actually turned out this is the positivity rate. It's pretty good. Again, none of that's fit. So early on, there's a lot of stuff going on that we didn't really get there. And that's something we can investigate. But then the bulk of it, up until that fourth wave, which again is kind of mysterious, it actually aligns pretty well with the positivity rate. And again, that's not fit. So we were pretty happy with that. The seroprevalence data, on the other hand, though, was not so good. And this is something we've had a lot of conversation about. So the green is the data from Canadian Blood Services, and the red and blue are from the model. And so there's a lot of conversations we've had, both on things we can criticize the data for. So it is Canadian Blood Services data, which means you're talking with people who are volunteering to give blood, which likely represents a very responsible subset of the population. Another thing is that our model is not age structured at the moment. At this moment, it wasn't. And so everyone's kind of lumped together. And of course, the blood donations are 17 plus, but our model, of course, captures all infections. And so that's something we can consider. And so it's a question of, what is it? We don't know. It's something we're talking about and how we're exploring our model further to see if we can capture it. But it also brings up an important question of identifiability in modeling. So when you have a model, and you have data, and you have all these things that you can use to fit, and the data fits pretty well. And then you have other data which you don't fit, and it's pretty good. So you can start to ask yourself, how could we change the model to fix this, right? If you have all these things that fit pretty well, and you get one thing that doesn't fit well at all, there's this question of identifiability that could be coming up. And so it's sort of interesting. It starts to ask questions of, well, what could we do differently? What kind of data do we need to capture to adjust the model to sort of pick this thing up? So, yeah. And so then something else we can ask is that reflect part. And so we have these models and we can look at them and say, well, how did we do with different strategies? Given that we have data, we fit parameters, that's sort of what really happens. So we can look at different scenarios. And so going back to that original model, we can use it. We use it for the other models too, but I'm going to show results for that original model in the early days. There was a question of how good or how did we do the right thing with the measures that were used. And so we defined some metrics. One is what we called the healthcare cost. So remember we had the cost, which was the relaxing cost. We defined a healthcare cost. And this is idea where we were talking to people, and at least at the time, and it's probably still true, that if every province sort of has a critical number of beds, this is the number of beds that they can have in a hospital for people who need to come in. And generally the idea was as soon as your hospital capacity exceeded 50% of your maximum, it was bad. Things were hard, and resources were going to have to be managed in a dire way. And so what we did is we said, well, let's define this healthcare cost where we integrate the active cases from a lower bound of time, which is the time, if it exists, where we exceed this threshold, critical over 2, and then up to a time t1, which is where we go below it. And there could be multiple times of that, so we have a potential sum. And we did this because it doesn't just capture, we had this conversation of how to do this. We did this integral idea because it was this question of, is it really bad if you have a lot of cases for one day, but yesterday and tomorrow are fine? And that probably is terrible, but it's probably just as terrible as if you have a high number of cases, not as high as a single day necessarily, but a relatively high number of cases over many days that has this sort of integrative effect on the hospital resources. So that's why we did it that way. And then we define this kind of total cost as this weighting between the health costs and the distancing cost. And this H infinity, so C infinity, we had to sort of pick as some maximal cost that people could endure. The health infinity cost is a lot easier to define, and we said, let's define it as this integral that we have here if we do nothing. So if all distancing is turned off and people just live their lives, we'll call that sort of the worst outcome. And so that's what we call H infinity. And so here's the different kind of plots with different weightings. I'm just going to focus on the bottom right, because that's just thinking of the health cost, which is kind of easy to focus on. And we got a really surprising result at the time, at least. So the way to read this is if you go left to right, that's increasing sort of the cost people can endure. So that's like pumping money into the system. And if you go bottom to top, that's increasing vigilance. So this is the number of cases that are required for you to social distance. And so as that goes down, which is going bottom to top, then that means fewer people have to get sick for you to take it seriously. And so why we got a surprising result, which I've circled at least in the first column here, is what you notice is that as I become more vigilant, at least in this scenario, it gets worse, right? We divide by this H infinity, so 1 is the worst, dark red. And so we thought about this for a while, which is why is that? Why when you're more vigilant do you get worse outcomes? And then we noticed that in certain scenarios, actually, you can find local minima. So you can see in this case, the health cost is going down as you become more vigilant, but then it goes up again. And so here's a kind of example of just mechanistically how it can happen. And this is the idea that this is this integral coming into play. So you see, the graph's kind of ordered funny, but the red, it goes red, then blue, then green in terms of least vigilance to most vigilance. And you do indeed see that just from the peak value, it goes, well, it does go down and back up, but you can see this effective peak is there, but this integrative effect comes in as well. And so you see it can actually be really wide. And so even though you can cause cases to come down by being more vigilant at its peak, maybe, you might endure it longer. And so that integrative effect comes in. And so what I wanted to say quickly about that is, you're thinking, why is this? And it turns out what happens in the mechanism is that why this, you can kind of think this makes sense, because we have this cost aspect. And because as you stay home unnecessarily, you're building this cost, right? So if you're not sick, you're building this cost up. And everyone has a maximum cost they can endure, and so then they relax again. And so what happens is if you're too strict, if you're too vigilant, everybody stays home, let's say, they reduce their contacts, and we just have a lot of healthy people staying home, building up cost. And then they come back, right? Cases come down, they come back, but because they've endured this cost for a long period of time, when cases grow again, they're not as willing to go back to relax, to distancing. They're not willing to reduce their contacts as much. And so essentially what happens is, now when cases get really bad, you don't have this mechanism to protect people anymore. And so you get this worse outcome than if you'd let them be more relaxed at the start and sort of spread the cases out. So this was actually picked up by the media there was this whole interview trail where they were talking about, because we were kind of advocating for shorter but more frequent lockdowns at the time, and it was around the time there was this whole debate of lockdown, so it just turned out to be this thing. But it also got us to ask the question, which is, when we saw this local minimum going on, we thought, well, interesting, we can think of this parameter and say, what is, and this is back when we had a 1 fit to that early data, right? So there's just one parameter. What is the best number, right? Because there is, for a given cost scenario, a given C, there clearly is a local minima. And so that's what we did here, is we said, okay, let's just look at this health cost, and let's look at this critical parameter. So this is the percentage of people of the total population who have to be sick for me to take it seriously and want to reduce my contacts. And as you go off to infinity, you expect it to go to 1, which it does, right? Because again, as it goes to infinity, that's nobody doing anything. Is I require everybody to be sick. Okay, not really infinity, 100%. As I go to 100%, if everybody needs to be sick for me to do something, then I'm not doing anything. And so that's how H infinity is defined. And so that makes sense, that goes to 1. And you see this other spectrum, it's shooting up to 1 at the far left, and this is the idea of 2 compliant, where it's also going up. And so you do indeed get this local minimum, which is in some sense, if you want to call this the healthcare metric cost, the important cost, that's where you should sit, right? If you do less than that, it's worse. If you do more than that, it's worse. And then the black dashed line is the value we fit to the Ontario data. So in some sense, that's saying that Ontario did too much, right? If you're to the left of this, you did too much. If you're to the right, you did too little. And so something we want to do, which we haven't done yet, we're trying to get a summer student, is to look at this for each province and just kind of get a sense of how did each province do based on their data and their values that we can fit and this similar curve for them. Okay, so the last little bit that we've moved on to, and this is that reflect piece now. So now we're going back and we're thinking, okay, everyone talks about these structuring models, and often it's this age structure, but we're doing what we call compliance structure. And some people use the term counter-factual. And so this idea of, now that we know what happened, what if people did different things? And so what if people behave differently? So we have that vertical transition. We have a second group of it now, which we call people who are kind of counter-compliant. And we have different scenarios. So there are people who either do all the distancing we have. So 0 means they won't distance at all. And distancing just means reducing contacts in the model, which could of course generally mean even wearing masks and things. Up to our maximum, so that's D2. And V or no V, so either vaccinate or don't. So the top, D2V, that's what we've been covering so far. That's everybody does everything they can in the model. They'll use the NPIs as effectively as they can. And I mean, still context on the data and their behavior. They'll go up and down the spectrum. And they'll get a vaccination. And then we sort of go down the list of the different people who do and don't do different things. Okay, and so these are some of the preliminary results that a postdoc's getting into. And so this is hospitalizations. This is if you assume that 20% of the population will fall into this group of people who don't want to comply. Okay. And so you say, well, what if 20% are in D0? What if 20% are in D0V? What if the 20% are in D1, et cetera? And then everybody else is in this D2V. And so this is cumulative hospitalizations from the beginning of the pandemic till now. And you see, unsurprisingly, that it gets worse as you do less. But what we see is the NPIs have a much bigger impact than the pharmaceutical, because the bars next to each other, that's vaccine or not. So brown and purple is the same distancing level, which is none, and vaccine or not. Red and green, same distancing level, which is 1, vaccine or not, and same with blue and orange. So it's the NPIs that have the bigger issue than the PIs. So it was cumulative. So what we wanted to also look at was the waves. So these are defined as the disease waves by the province of Ontario, up until we went as far as the end of 2021, just because Omicron comes in, and that's a whole other game that we're talking about separately. And so these were the disease waves as defined by the Public Health Agency of Ontario. And so those are just the dates. And so that's what refers to timelines at the top here, time period 1, 2, 3, and 4. Okay. And so you'll see, interestingly, that, and the vaccines, by the way, don't come in, if you go back to here, the vaccines really don't start coming in till wave 3-ish, right? That's when that mass vaccination kind of came into play. And so the first 2, that's why they're just parallel across. There is no vaccination yet. And so you'll see how the cases, this is hospitalizations break down. It's in the second period where you see the real benefit of distancing. But even as you get to the 4th period, that's where vaccines start to matter. You can see that's splitting off because the vaccines take time to spread around the population and you take time to build up the population level. But that's where you see it starting to emerge, that the vaccinations play a stronger role here. And so we showed the same with cases. We just picked hospitalizations recently. We've sort of switched over because, of course, cases aren't being counted really, and so hospitalizations are what matters. And you see a similar pattern in the cases. And so, just to give you a visual, because I think it's hard to think with bar graphs, but here's just those scenarios. So the dashed line is the data. The light blue line is essentially the model I presented up till now, and then everything else is these different scenarios. And so you can see you indeed get these much larger spikes for not complying with the distancing. Something that does impact it, and this is something we're trying to figure out too, is it's hard to define waves when you do this analysis, because of course, if you're going to let people not comply, and you get these sort of higher spikes in cases, they also happen sooner in some scenarios. And so the wave definition changes if you allow this non-compliance to factor in. But you see, you do get these big spikes, and then of course the waning immunity comes in, and you see a much bigger spike in which would have happened in the fall wave, because all those people got infected early on, and you see it really comes down. There's that period of time where actually it doesn't seem like anything really matters, because they all sort of overlap. And this is the idea that people who didn't get infected, or people who didn't distance or didn't vaccinate, got infected early, and a lot of them did, and so they were protected, right? So it's just like getting a vaccine if you never got sick. But then when their immunity wanes, they're ripe again for a massive wave later on. And so here's just a similar plot, which is because we're also exploring different fractions of people who do this. Okay, and so whether we have 20%, 15%, 10 or 5, and we're also going the other direction too, but they're not on here. And you see a very similar analysis. Of course, it gets worse the more you do it. And so part of it, you want to do this. So for instance, you take the 5%, you can see there's not that much difference. And so part of why we want to look at this in terms of the proportion that we're talking about is to see how do we message these interventions to the population. If you can show that if 5% of the population doesn't listen to you, and it doesn't have that big of an effect, or however it affects it, it's within a tolerance you're happy with, then that gives you an idea of how you can message it. You know, early on in the vaccination campaign, there was a lot of issue going on that only 90% or something are getting a vaccine, and people are mad about the 10% not doing it, and their neighbors aren't getting a vaccine and they are. And there's a lot of negative sentiment that circulates over people choosing to comply or not to comply. And so I think it's important that we look at the effect of non-compliance so that we can understand how to target public health messages, so that we can say, look, it's okay. Knowing there's going to be people who don't comply anyway, what kind of number do we care about? So if we're at 5% haven't complied, do we just let that be? Knowing that it's a lot of money and energy to try to even get them to change their mind, they may not. Versus if it's like 15%, that may be the threshold where you say, you know, we need to put resources in to try to get more people. So that's part of that. Okay, and so that's the summary. The transition to this model sort of went through that cycle, right? We started out, and then it evolved, and we did some predictions. And then we saw when the predictions failed, so we put more things in, and that informed us. You know, we're missing mechanisms like waning immunity in that case, and then we're reflecting on the model through some of these counterfactual analyses, et cetera. And of course, it keeps doing more work. So I talked about this impact of waning immunity, and so we want to look at that in a sensitivity analysis, because that's still something that people aren't sure on, really. With the seroprevalence data, we talked about maybe the importance of age structuring, so that's something we're talking about. And I wrote behavior modeling, which this is, of course, there's behavior modeling going on, but with a master's student I'm sharing at UBC Okanagan, we're trying to get into a bit more mechanistic modeling of behavior. You know, what drives people to change their minds about something mechanistically, so we don't just have to heavily rely on fitting some proxy parameter to data. And so I do want to mention, these are just the collaborators who I specifically worked with on these 3 models. Jane Heffernan is a colleague of mine at York University, and Yetta and Susan are 2 of our postdocs. But of course, as I mentioned, I have many other colleagues for the other literature that I just didn't talk about today. So that's that, and thank you very much for having me here. Are there any questions?
Any questions? Yes.
Just a very naive question, perhaps on the statistician, that so you get your data, you try to the model, you say, okay, it doesn't fit, so the problem should be in the model. So why would you say it's coming from the data?
Oh, I think that's the issue, is that it is in both. So I mean, especially the seroprevalence issue, I think the issue is the model probably, I mean, models are always wrong either way, right? But I'm very much subscribed to the data is also wrong camp. And I think it's bad when people stick to either story too strongly, right? You know, if you're like, oh, my model's perfect, the data must be wrong, or oh, the data must be infallible, so we need just this model. And I've seen that to an extreme level. I've seen people say look at, oh, we have negative numbers in the data, so our model must get negative numbers. And it's like, well, let's come on here. This doesn't make any realistic sense. But so I think in the seroprevalence case, that's why we're trying to explore both angles, right? And I think this is where the role comes in, where you have a model that has some biological mechanism, and you can say, here's what we think it's not matching. Someone tell us why, right? And as long as I think you're open to being wrong, then that's a fine thing to say. And I think too often we feel the need that things need to match perfectly when it's okay to ask scientific questions. So in that case, with the data, for instance, it's coming from CBS, so it's very skewed to people who are donating blood. It's limited to people 17 plus, et cetera. So there are some data issues there. There's also this idea of does the antibody measurement, is that really a metric for infection? Right, because there's other mechanisms. You can have false negatives. You can also have these T cell responses in your body if you have a strong infection. There's also a question of, if you have a mild infection, do you produce enough antibodies for the test to pick it up? Or if you have a mild infection and it's been long enough since you donated blood, do you no longer get detected by the test? So there are these questions that are kind of there, but yeah.
No, because some graph you got at the very left, data was just, I mean, it was not possible at the beginning, we didn't give any data.
Yeah.
You just get points, so we pretend that we got positive, but actually by no test. Then we got tests for all people that, so you didn't try to get a process to understand the production of data.
That's a good point. No, we didn't in that. You're right. In the testing data, especially you see that plateau at the, so that's exactly right. That's just NaN, right? No tests. And so we just put numbers in to make it there. But you're right. There's a question of how does the testing evolve? And you know, one of the things you have to ask is, if you get into those details, you have to realize the resolution of your model too, right? Which is we don't compartmentalize people based on age at that point, et cetera. And so you just have to be careful if where the scrutiny is going to go. So kind of take what we have, right, and move forward with that. And then part of the conclusion is what you say, you know. So in these time windows, we're fitting parameters for this reaction to sort of behavior distancing. And so part of the paper is describing what we interpret that to be. You know, very vigilant, people were being very vigilant, or they were being sort of relaxed, rather than the actual number we get. You know what I mean? So good question though. That's why I have great statistics colleagues too. Over here, help me. She knows data, yeah. And time series too. Any other questions?
I have a question. Your seroprevalence data. So the whole study was for Ontario, right?
Well, so that's from the Canadian Immunity Task Force, the CITF. So they produced this data.
So they have all.
They have it for all. We just isolate Ontario because everything else is we did for Ontario, but they have it for every province. And not all the studies are CBS. There are some other studies, especially in other provinces, and I think Alberta even has some data on children. And then we start looking at some of that data, you see bigger numbers than what's here. But anyway, that's just the Ontario CBS data. And of course, again, just the way that we considered, because once Omicron hits, it shoots up, right? And if you look at the vaccination data, this is the other thing that tells you something about the data, is you look at the antibodies and vaccination, which we didn't show, is it gets pretty close to 100%, which we know 100% of people didn't vaccinate, right? And so that's again sort of skewing this. Chances are people who are responsible enough to donate blood likely were responsible enough to go get a vaccine too, right?
The first time I saw this seroprevalence coming from blood donors, I thought this was a huge biased in something.
Yeah.
Because I don't think blood donors are representative of the whole population.
Yeah.
You're missing pockets of minorities and just behavior.
Exactly. I think so too. And I think that's a huge underestimation. I think, not saying our model's right, but I'm not worried about the discrepancy between the data and the model in that case.
But there is one study by StatCan on seroprevalence that is the most representative of the population. Otherwise, like all the studies done, I think by the immunity task are biased because it depends on the sample size. That
Do you have that data for Ontario? Or is it just
I
the
have
Quebec study?
only data for children in Montreal.
Okay. Because I would be interested in seeing some less biased data. Yeah.
Other questions, comments?
Sure, please. No movie though.
No, no.
movie.
So when I heard about this, blood donors being the samplers for circulating, I was reminded of this joke about the person looking for his keys under the lamppost.
Okay.
And he was asked, why are you looking there? Have you lost them near a lamppost? He said, no, but the light is better here. So I think the same thing.
Right. Right, yeah, yeah.
Okay, so thank you very much.
No problem, thank you.